Welcome to today's lesson. In this tutorial, we will be able to recognize graphs of parent functions given either an equation or a graph. We will also be able to describe the domain, range, and end behavior for each of our parent functions. So we're looking at the graphs of our parent functions, but before we begin, I'd like for you to complete this matching section. I've given you we're going to be exploring 6 of the parent functions. We've got cube root, absolute value, square root, linear, cubic, and quadratic. What I'd like for you to do is match these 6 names to these 6 equations over here. Pause the video at this time and do your best with this matching section based on what you already know about these vocabulary words and these symbols. If you want to just use a pencil just in case you mess up, that's fine, but please pause the video now and complete these 6 matching questions. Pause now. So thanks for doing that, and here are the 6 correct answers. Let's talk a little bit about this. When we're talking about a root, we've got a cube root and we've got a square root. That, of course, is our little root symbol. The cube root has a 3 tucked inside here as the index, and the square root is simply the square root symbol that you've already seen before. The absolute value functions, the graph will look like a V, and the absolute value bars, of course, look like these bars. The linear, the cubic, and the quadratic is just a difference in exponent. The linear is your basic function. There's actually no funny symbols going on with the linear. It's right here, just y equals x. That's your linear. That's just a line. The cubic has an exponent of 3 as a cube, and the quadratic has an exponent of 2. And there's your quadratic. It's an x squared. So hopefully you did well with this. It's going to be important for you to be able to match these graphs and these equations to the words. Now let's talk about graphing them. What we're going to do is we're going to choose appropriate input values. That's values of the x, the domain, and we're going to generate a table of values. The first time we look at each of these patterns, we're going to just do that with a t-table. After we've done it, I'd like for you to memorize what the pattern looks like and be able to just go straight to the pattern without having to do a t-table. So the first one that we're looking at is just your basic one, y equals x. That is your linear function. It's just going to be the graph of a line. Now to generate our t-table, we get to pick whatever we want for x. So I'm just going to pick a couple negative numbers, -2 and -1. I'll pick 0, and I'll pick a couple positive numbers, 1 and 2. Again, you can pick whatever numbers you want for the independent variable. This is your domain. The y is going to depend on what we've picked for x. In this case, it's really not that difficult because it says that the y's are equal to the x's. So whatever we had for x, y is going to be the same exact thing. So they're actually the same numbers. This has given us 5 ordered pairs that when we plot them will be the pattern of this basic linear parent function. So let's graph these ordered pairs. -2, -2 is a point right here. -1, -1 is right here. 0, 0, of course, is the origin. 1, 1 right here, and you can see the pattern. These are the 5 dots that we generated, and we can see that the pattern is going to continue in this linear fashion. I'm going to connect all 5 of these dots together and make a nice, hopefully straight line. There's your basic linear function. Now, of course, we have plenty of practice in Algebra 1 with changing the slope and the y-intercept for all of our lines and graphing those. This is your basic linear function. Let's state domain, range, and end behavior. Domain, we're always going left to right. So I'm going to start at the far left, and I see that this graph is starting all the way down here at -infinity. And we're going to be going all the way to the right, which is +infinity. This graph has a domain of all reals. So I can do it in interval notation from -infinity to +infinity, or I can do the set of all real numbers like that, whichever one you prefer. The range is going up and down. I should say down to up. We always start as low as we can go, which this arrowhead is pointing all the way down. So -infinity is where this range is starting, and it's going to be going all the way up to +infinity. So the range is actually identical. The set of all reals. End behavior, remember end behavior will always start the same. I like to first describe what's happening on the left side. I'll start that sentence, and then I like to start or do what's on the right side. So as x approaches negative infinity, that's our left side, let's see what's happening over there. The left side, the function is pointing down. So I'm going to say that y goes to negative infinity. That's what it means, points down. On the right side, as x approaches positive infinity, that's all the way over here on the right side, the graph is pointing up. So y is going up to positive infinity. And there's our linear function. Let's look at our second function. Now I see my absolute value bar, so this must be the absolute value function. Absolute value function, the graph is going to look like a V. I always remember that because V is in the word value. I'm going to still pick x, whatever I want for x, and I'm going to pick the same things, -2, -1, 0, 1, and 2. Again, this is just an independent pick. I can pick whatever I want. But y is going to depend on what x is. If I have -2 as an input, the absolute value of -2 is +2. The absolute value of -1 is +1. The absolute value of 0 is 0. The absolute value of 1 is still 1. And the absolute value of 2 is still 2. So again, we've generated 5 ordered pairs. Let's graph them. -2, +2 is here. -2, 1, 0, 0, 1, 1, and 2, 2. You can see that because we're talking absolute value, when we pick negative inputs, absolute value of negative is still positive, and we can see that's what bends it up and becomes a V. And we can continue that pattern, and there is our absolute value function. If we're talking domain, as far left as I can go, it's going all the way to the left, negative infinity, and it's everywhere in between all the way as far right as possible, which is positive infinity. So the domain here again is all reals. For range, I'm looking as far down as we go. This time we do have the lowest point, which is right here at 0. So we're starting here at 0. We do get to include it. So I'll say 0 with a bracket, and then we're pointing all the way up to infinity. So we don't stop there. If we wanted to do set notation, we would do all y such that y is greater than or equal to 0. And our end behavior, again, I can always start the same way every single time, describing what's happening on the left side and describing what's happening on the right side. Now let's go and see what happens. On the left side, my graph is pointing up, so therefore y goes up to infinity. And on the right side, the graph is also pointing up, so y goes up to infinity. So we've got our linear function and our absolute value function. That's 2 of them. Let's see what's next. Y equals x squared. I see the squared, so I know that I'm talking about the quadratic function. The quadratic function. I'm going to choose the same 5 inputs, -2, -1, 0, 1, and 2. And now let's see what happens. When I pick an x this time, I have to square that input to get my output, my y. -2 squared is 4. -1 squared is 1. 0 squared is still 0. 1 squared is 1. 2 squared is 4. Let's graph these 5 dots and see if this is enough to see what this pattern is. -2, 4. 1, 2, 3, 4. -1, 1. 0, 0, 1, 1, and 2, 4. So that's 5 of our ordered pairs. I feel like there's more that we could graph. I'm going to pick 2 more inputs. What if I picked another negative, -3, and another positive, +3, just to see one more set of points. -3 squared and +3 squared are both 9. Let's graph those. -3 and then 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look at that. It just barely fits. And the same thing over here. +3, 9. We can see now definitely that this is not straight lines on each side. In fact, it is a curve and it is our parabola that we've seen before. It's not a V, I guess it's more of a U because it is curving upward like that, and that is our parabola. That is our quadratic function. The domain, range, and end behavior are going to be identical to the absolute value because we can see that the arrows are pointing as far left as possible and as far right as possible with everything in between. That's why the domain is going to be the same exact thing, negative infinity to positive infinity. Or if you choose set notation, the set of all reals. The range, the lowest value we have is the value of 0, and we do get to include it again. And we go all the way up to positive infinity up the y-axis. Again, if you wanted to do set notation, that's fine. All y such that y is greater than or equal to 0. And the end behavior I can see on the far left end, the graph is pointing up. On the far right end, the graph is pointing up. So let's describe the left side as x approaches negative infinity. The graph, which is y in this case, goes up or approaches positive infinity. And the right side, as x approaches positive infinity, that's the right side of the domain axis, y is also pointing up to positive infinity. Okay, let's look at our next one. Y equals, now I see a square root symbol, so this must be my square root function. Important for you to be able to spell the names of these parent functions. Here's our square root. Now the same sort of thing. I'd like to plug in a -2 and a -1 and a 0 and a 1 and a 2. But let's see what happens now. If I plug in a -2, what's the square root of -2? You can try that on your calculator if you wish to, but we can't do that. It doesn't exist. It's not a real number. We can't have a negative number underneath a square root symbol. Same thing for -1. I can't do that. There's not going to be, I can't plug in any negative values into a square root function. I can plug in a 0. The square root of 0 is 0, so that's fine. By the way, these are null set symbols. This means that it doesn't exist. You could say none or just nonsense. There's nothing here. I could plug a 1 in here. The square root of 1 exists. The square root of 1 is 1. What if I plug in a 2? The square root of 2, well, I know that I could get a decimal approximation, but I really don't know what that is offhand. I would need a calculator. So maybe 2 isn't the best idea. Maybe the next number that I would plug in is not even a 3. How about 4? The square root of 4 is a nice number. It's a 2. And then maybe I'd skip 5 and 6 and 7 and 8, and maybe I'd plug in a 9 next. Again, you get to pick whatever you want for the x's, as long as they make sense to plug in. I can take the square root of 9, which is 3. These are some nice values. I'm not going to plug in a 2. I'm not going to plug in any negatives. I'll just plug in perfect squares. 0, 1, 4, 9, 16 if I wanted to. So my first point is 0, 0. My next point is 1, 1. My next point is all the way out to 4. 1, 2, 3, 4, and then 2. My next point is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 before I go up to the 3. And you can see that these numbers are sort of the reverse of what we just did over here with the quadratic. You can see the 1, the 4, and the 9 as outputs for the quadratic. Now they're going to be inputs, 1, 4, and 9 for the square root. We don't have anything over here in negative land. We start right here, but then this pattern will continue all the way forever that way. So now when we talk about domain, finally we have a domain that's different than all reals because we don't have anything over here. In fact, the very first part of the domain is 0. So I'll start with 0. I do get to include it with the bracket, and it'll go all the way to the right to infinity. So there we go. Or that's all x such that x is greater than or equal to 0. Remember, you get to take your pick as to which one you would prefer. The range, the lowest point on my graph, is also right here, which is 0. And then it goes all the way up. It looks like it's slowing down, but it is going up forever to infinity. which would be the same exact thing here, except we're talking about y, such that y is greater than 0. And finally, my end behavior, as x approaches negative infinity, well, actually, nothing's really happening over here. So there's not really much of an end over here. So I'm not even going to describe the left side. It's really just about the right side. So as x approaches positive infinity, y is going to be pointing up. So we are pointing up. So this end behavior is a little bit different as well. I'll put a little star here because we're not really talking about both sides. We're just talking about the far right end. Okay, so we have 2 more to go. Let's now talk about this one. Now I see a cube, so that must be the cubic function that we're talking here, y equals x cubed. I'm going to pick the same starting points, -2, -1, 0, 1, and 2. I understand that now I'm going to be cubing these numbers to get my outputs. So -2 times -2 times -2 is -8. -1 times -1 times -1 is -1. 0 cubed is 0, 1 cubed is 1, 2 cubed is 8. So that's a good way to just generate 5 ordered pairs that are on the cubic function. And now let's graph those. -2, -8 would be to the left 2 and then down 8. Let me make sure I counted that. 1, 2, 3, 4, 5, 6, 7, 8. Yep. Then -1, -1, 0, 0, +1, +1, and then +2 and up 8. So that's an interesting looking graph. And it starts way down here, sort of curves right here in the middle at the origin, and then continues all the way up like this. That is your basic cubic function. The domain, again, your eyes are looking left to right. I know that this arrowhead is pointing down, but you have to also understand that it is pointing to the left. That's why the domain starts at negative infinity and it goes all the way through to positive infinity. All reals again. There's my all reals. The range, that's pretty clear to see because again, we're pointing all the way down and we're pointing all the way up. So that's all reals as well. And end behavior, we do have 2 ends. I'll describe the left end, and then I will describe the right end. This is always the same for any function. It just depends on what is y doing on each end. So let's say when x goes to negative infinity, that's the left end, and we're pointing down, so y goes down. And as x approaches positive infinity, that's the right end, and y points up. So there's our end behavior. Hopefully domain range and end behavior is getting maybe a little bit easier for you. And our final parent function is the cube root. I see my root symbol again, but because I also see that little 3 hiding in here, this is the cube root function. And very similar to the square root function, I don't want to just plug in anything for x. I know that I can, but I want to plug in smart numbers for x, numbers that are going to help me. Now, cube roots, since there's the odd number, we can have a negative underneath here. And in fact, what I'm going to do is I'm going to pick these 5 outputs and put these as inputs. -8 is a perfect cube. -1, 0, +1, and +8, these are nice perfect cubes. If I put a -8 and take the cube root of -8, I'm going to have -2 as my output now. The cube root of -1 is -1. Cube root of 0 is 0. Cube root of +1 is 1. And if I put an 8 in here, the cube root of 8 is 2. I can put a 5 in here if I want to, but I don't know, without a decimal approximation, what the cube root of 5 is. So I'm not going to put a 5. I'm going to skip from 1 all the way to 8. Now let's plot these 5 points and see what the cube root function looks like. -8, -2. Now we go all the way over here. 1, 2, 3, 4, 5, 6, 7, 8. And then down 2. -1, -1. 0, 0. +1, +1. And then all the way out here to 8, before we go up to the 2. So it's pretty similar, except that it's kind of flipped over. Now we're still wiggling right here in the middle. But the cube root function kind of looks like somebody swimming in a pool, maybe. The domain is pretty easy to see. We're going from negative infinity all the way through to positive infinity. Yet again, all reals. In fact, of all 6 of these parent functions, only one of these domains is different, and it is that square root function. This is the only domain that is not all reals when we're talking about our parent functions, at least these 6 parent functions. The range might be tougher to see. I know that it looks like this is pointing all the way to the left, but understand that it's also pointing all the way down. So it starts at negative infinity, and we're going all the way up to positive infinity. So that's all reals as well for the range. And then end behavior, one last end behavior. Let's describe the far left end. Let's describe the far right end. Y is going to be doing something at each end. The far left end, here we are, Y is pointing down, so negative infinity. And the far right end, Y is pointing up to positive infinity. So those are the 6 parent functions. It is important for you to understand how to write the name of each of them, what the special symbol in the equation looks like to be able to identify the name, and what the special values are that came from this t-table so that you can graph these 5 values every time. We also describe the domain, range, and end behavior for each of the 6, and that's good review. Thanks for watching this tutorial. We'll practice this in next class. Thank you very much. I'll see you then.